Hello and good evening everyone. Welcome to this year's Lakshmi Raman Memorial Lecture. This lecture is sponsored by the family of Dr. Lakshmi Raman, who completed her PhD in crystal dynamics from our department, that is the Department of Physics, IIT Madras. She then went on to do her postdoctoral research at various institutes, including ETH Zurich and University of Texas. She worked in the telecommunication industry and has worked with Bell Labs for a long time. She was internationally recognized expert in her field. Throughout her life, she remained deeply committed to the higher education of women. And every year, we invite distinguished faculty for this lecture. Today's lecture will be delivered by Dr. Vani Vemparala, Professor of Physics from Institute of Mathematical Sciences, Chennai. Her work integrates statistical physics and molecular simulations spanning from atomistic to coarse-grained scales to study polymers, charged macromolecules, glassy soft matter, biomimetic antimicrobial systems, and membrane-protein interactions. She is particularly interested in uncovering minimal physical principles that connect biological and soft condensed matter phenomena. Please join me in welcoming Dr. Vani Vemparala to the stage.
All right. First, I want to thank Prabha and Rajesh for inviting me to give a lecture here, Lakshmi Raman Memorial Lecture. I'm Vani Vemparala. I'm from a neighboring Institute of Mathematical Sciences, which is just 10 minutes away from here. So today I want to talk about, this is some work we have been doing in polymer physics area, where we are interested in understanding how do polymers behave in crowded environment. So the main question one is interested in is how do they behave? If you have a single polymer, you can think of something like if there are a lot of crowders, there is phenomenon of collapsing from an extended to a globule conformation. Or if you have multiple polymers, how do they aggregate? Basically, what are the ways in which polymers talk to each other or within themselves when they are in a very crowded environment? So that is the main question one is interested. So since this is a colloquium, I was told that I should have a little more introduction to, because there may be many people who may not be from the area of simulation. So I just thought I'll just give a brief introduction and context of where simulations in general and polymer simulations in particular, where do they fall under. So in general, how do we understand complex systems? There are many different levels. The simplest is theory. Theory as in you can have, you can identify universal principles, you can get many kind of scaling laws, limits, asymptotic limits about the things. So you can get vast insight into out of these questions as to why some phenomena may happen. But of course, the limitations are it requires heavy simplification. There are no microscopic details which may be very relevant to a lot of important phenomena are missing from it. But that is one lens in which you can probe the system and try to understand. And the second part obviously is experiments. Of course, the best aspect of experiments is that you have a direct observation of a physical behavior. You have all interactions are present. Sometimes you can get counterintuitive phenomena. You have the observation, you have the data. But of course, times it's very difficult because of the lot of parameter sets may be mixed, and then how do you isolate the system could be hard. It may be you can still design experiment, but there is some amount of isolation one is probably difficult to do. And then simulation sits somewhere between theory and experiments. So you have a control microscopic access into how a system behaves. You can tune interactions. You can ask questions which, for example, may not be amenable to experiments, but you could get physics of the problem by actually tuning certain parameters, even when it may not make sense in some sort of experiments, but you can get a lot of insight into it. Also, you can have a very microscopic detail of how these simulations can work, and they can act as a bridge between theory and experiment. Of course, they also have limitations, which is computational cost is the biggest limitation for that. How do you accurately represent a particular phenomena of your interest? it requires not only a lot of computational cost, but probably you are then limited by how big a system you can simulate, right? So there are limitations for simulations as well, but that is the lens through which my work is largely informed, and we need all the three. The question is, how do they answer different layers of the same question. So to give a very simple example, especially the problem of interest here, suppose if I look at polymer collapse as a model problem in which I want to look at this. So this is a very simple phenomena to understand, probably many of you have seen it, which is that if I take a macromolecule and I put it into some kind of a solvent, depending on the interaction between the polymer and the solvent or the polymer-polymer interaction, I can tune it to go from a extended to a collapsed state. If it prefers solvent interactions, it tends to be in an extended state to maximize its interaction. Otherwise, it can go into collapse. So this is a simple thing called coil globule transition. I can look at it from a theory point of view. What does theory give me? There is something called a Flory theory that exists to explain polymers. It can give you, you can write the free energy, and as you know, all of us who have taken StatMech courses, once you know free energy, you can calculate many properties. Thermodynamic properties of it. But so you could write a free energy expression for this, and then you can get some scaling laws. What are the scaling laws? How does the effective dimension of the polymer behaves if it is in a good solvent? It scales as n to the power of 3/5, where n is the number of monomers. Or you could, or if it is a globule, it grows as n to the power of 1/3. So you could get some kind of a scaling laws and some kind of a free energy you can write. That's the best description you can do with the theory. You can also look at this from an experimental point of view. So this is a very nice experiment, dynamic light scattering experiment, in which you could measure the this particular polymer polyacrylamide collapse you could measure. And again, this is a direct visualization about how you could look at a collapse of the polymer. But of course, as you can imagine, in both of these cases, the microscopic details is what is missing. You can do simulations, and now you could do a direct visualization of the collapse pathway. So you could go from extended, you could sort of look at the system at whatever time scale of your interest, and you can see every detail about how this particular polymer, for under certain conditions that may be not relevant now, whatever are the conditions, you could look at an atomistic picture and try to understand how does it go from an extended, let us say from an extended to collapse conversation, what is the trajectory that this thing follows, what kind of contacts are made. So you could take a simple polymer like this, and again these three lenses are giving you three different kinds of information, and depending on what is the information one is relevant or what is it, you could choose one of the things. So what do we try to do when we try to do predictive models? We go from physical systems. We have a system, and the systems behave in certain way, and our goal generally is to understand two things. One is to understand the system and their behavior. Why are they behaving like that? And of course, a bigger goal usually is that once I understand these things, why they behave, can I predict some things, which from whatever is my understanding of this is, how do you do? Systems and their behavior, you could again ask whether it is a specific question you are asking. Specifically, let us say I want to understand how water and ice behave. So you are now saying specifically this particular solvent I want to understand. Or maybe you want to understand a very general question. How does a liquid or solid to liquid phase transition behave? So these are very different kinds of questions. I hope you are able to understand, as in what kind of a resolution that is required to answer these things. And then depending on the question, you build an appropriate physical model. You use the required equations. For example, again, as you all know, depending on whether a system is classically amenable or quantum mechanically, you either use Schrodinger equation, or you can use Newton's equations, classical equations, and then you solve, you measure observables. The usual inputs into these things are classical mechanics, statistical mechanics, EM theory, everything very basic that you have dealt with. You predict properties, and if it allows you, you have experimental results also as an input to build your physical model, and you can compare your observables with the experimental results, and you could have an optimization sort of a loop in which you could reasonably show what the experiments are, and then you could go ahead and predict. So this is a very generic model. So how do we do with the question in this in particular? You have an interaction potential or a Hamiltonian, you know the system, you have to describe the system on a computer, what are the interaction terms that go into it, what are the boundary conditions. Essentially boundary conditions are what kind of statistical ensembles you will solve this problem in. Depending on the model that you are using, you would have different, I'm assuming you've all had StatMech in some form. So you could look at, ensemble is just a very fancy word, it's just nothing but what is a boundary condition under which you solve your equations of motion. Is a system closed system or an open system? Depending on that, you could use different kind of an ensemble. And of course, the resolution level is important. Then you select a sampling scheme. Again, maybe this is something some of you may be familiar with. You could do a molecular dynamic simulations or a Monte Carlo simulation. You generate your trajectories and you do your compute observables and try to predict some kind of models. Again, so I've been saying using the word resolution. So what resolution exactly means? You have a time scale on the x-axis and you have length scale on the y-axis. So there are different techniques that have been developed depending on what kind of a particular, in this phase space of length and time you are in. My particular interests usually lie in all atom simulations and coarse-grained simulation. I'll explain that in a bit, what is the difference between the two. You could, if you have some phenomena, you could also do things like DFT, quantum mechanical, or you could do very large mesoscale simulations as well. But this is the place in yellow is what I typically work in this. So the coarse-grained resolution from all atom you can see very easily. Suppose if I have some kind of a polymer with all atom description given, I have carbon, hydrogen, oxygen, everything. Now I could do coarse graining at multiple levels. I could just say that I absorb all the hydrogens and call that as one monomer, or I could do all the functional group, each functional group is one monomer, or a monomer itself I can represent as one site of interaction. So depending on the question, I could go from one to the other. A natural question that should arise, if it has not already, is that what tells you, what informs you that which resolution is it that you can? And that's a very important question that depends on the system of interest, the question of interest, and what is a phenomena that is amenable to any of this kind of resolutions. So in equations, where does this resolution go into? What we essentially, the resolution goes into what is called your interatomic potential. So basically interatomic potential is nothing but the description of the system on a computer. Now I have to tell the computer that, for example, if I am taking a polymer, these two monomers are bonded together, there is some kind of cause to bend three of these things, or you have a torsion thing that can happen, there are charges, then you have Coulomb. So every detail about what your system effectively is hidden in your interaction potential. You could have something called an all atom resolution, where it's extremely detailed, many body interactions, you put everything, all the details. Or you could have a simple bead spring model in which you say, I will ignore all the details of the system, I simply connect it as a bead spring model, and I just say there's an excluded volume and there is connectivity. That's all I will put into the system. Can I still get some physics out of this? So what changes from one to the other? Clearly you can see the number of degrees of freedom are much, much smaller, which means now you can do larger simulations. The functional form of potential changes, and the mapping of the time scales changes, but effectively you are still probably going to solve the same kind of equations or probability. Coming to sampling methods, you have two kinds of sampling methods. Again, from your StatMech, you must have seen you have an ensemble average of a property or a time average of property, and ergodicity tells you that if you do these simulations for long enough, your time average should be same as ensemble average. So whether you do an MD simulation or a Monte Carlo simulation, technically there should not be any difference in terms of your results, and the only difference is which is more suitable to do a problem. Other than that, there should not be any difference. I am someone who does molecular dynamic simulation, so this is just the different ways, but I do MD simulations. So now polymers, many of you probably don't need the introduction, but The way I look at these polymers are, you have two kinds of things. I work on both these polymers. One are very synthetic polymers, which you have plastics, hydrogels, polymer blends, you know, plastic bottles, PET, any of these things. There are also biopolymers. Your protein DNA are also polymers. And then you have your actin filaments. So you have a lot of those kind of polymers also are there. And depending on the question, so I divided some sort of questions which probably require atomistic details, are something like, how does a particular molecule bind to a protein? Now this probably I can't just do some kind of coarse grain simulation. I probably need all the details of atomistic thing. Or let us say some kind of hydrogen bonding. Again, I have to put hydrogen in it because I'm interested in hydrogen bonding, which means I cannot do coarse graining for these systems. But maybe if I'm trying to understand in general, if I take a protein and I just initially when it is formed, before it takes some very textbook formation like this, if it goes from extended to collapse, probably I don't need all the details. In that kind of question, I can probably get away with using a coarse grain simulation. Another aspect is that you have a lot of polymers or probably even protein aggregation. The scale is too large for any atomistic simulation to give you any meaningful results. So then the question is, can I get away with not involving all the details, just treating them as polymers, maybe even charged polymers, and can I look at the aggregation of these things? So again, these kind of questions in which you can have crowding effects, you can have aggregation, phase separation and things like that, probably coarse grain description is something that is more meaningful. So the main takeaway I think is that it depends on the question you ask. So there's no meaning in saying I do all atom or coarse grain. The question is, what is the question one is trying to ask, what level of detail is needed, and what lens do I take, whether I take atomistic or coarse grain simulation. So this is a small set of different problems I do. I work across resolutions. So I look at a lot of cell membrane problems, interaction of polymers and proteins with cell membranes. I look at protein functions and some mutations in protein function, and how does water, and how if you dissolve in solutes in water, what is the structure of water. So as you can see, these kind of questions I have to put in all atom resolution. So this is some examples of problems I do where all atom resolution is needed. I also work in coarse grain simulations in which the idea is to understand if I take charged polymers, how do they aggregate, what kind of aggregation mechanisms are there. There are recently started working in something called biocondensate or liquid-liquid, the systems where you can have this kind of separation of phase separation of liquid-liquid, where you have condensation and crowding effects. These is not possible to do atomistic simulation, very expensive, and probably you also don't need because you are looking at very generic phenomena. I also work on ring polymers used as materials. In terms of materials, these are, the interest is to understand they behave like a glass, they behave like jammed systems. How do you understand the glassy dynamics of this ring polymer? So there is a span of both scale and time resolutions that I work in. Particularly in today's talk, I would be focusing on coarse grain simulations and trying to understand if you have some kind of a crowded environment where there are attractive interactions present, what are the kind of phenomena that comes up. So here is a nice example of what is the earliest coarse grain polymer simulations that I could find. This was back in 1975. Of course, historically people were doing bead spring models simply because of computational cost, because computation was very expensive. So you would try to do very simple model. This was one of the first papers I could find. I couldn't find a paper earlier than this. In this model, they are looking at liquid N-butane, but it's a very simple model in which you have Lennard-Jones potential and some kind of a connectivity and bending potential. That's also, this is the earliest simulation I could see, and I think they did it for, I don't know, 1,000 steps or 1,500 steps or something of that sort. It's a very nice paper. I mean, if anyone is interested, yeah.
So when you go from the all atom to the coarse grain, is the coarse grain potential something that can be systematically derived?
Yes.
Or is
Yeah.
it like phenomena?
Okay. Answer is yes, you can, but that's not what I do.
Okay.
So to answer the question, so there is a way in which, suppose I am still interested in particular nuances of an atomistic system, but I don't want the computational cost. Let's say that is where I'm sitting. I cannot remove all the detail. Then I have to do effort in which there is a very systematic way in which you coarse grain and show that this coarse grain is actually, basically what you're doing is, when you do the phase space calculation, that phase space is just renormalized phase space of your atomistic thing, and I have to prove first that this is the case. But as you can see, if I just change a different system, I have to do this whole thing again, which means in some way what I'm saying is it's not transferable, right? What the kind of simulations I do is I throw away even that detail. So I am not simulating a polymer, particular polymer. I am simulating polymer as a family. So in the way I simulate, only the, as I said, the connectivity, excluded volume, and the principle of what is the problem, the generic principle is only the input. So when I say I'm doing a polymer, that polymer is not representative of anything. It is just a representative of some class of polymers. So people do what you are saying, and it's an extremely labor-intensive work, because it's not something you have to first show that there's an exact mapping. Just because you've asked a question, I'll tell you the other way. As you can see, the reverse problem is very difficult. You could imagine that maybe if I need to reach 1 microsecond simulation. I have a atomistic thing, I coarse grain it. I do coarse grain simulation, which I can do very fast, reach microsecond, and can I map back to atomistic? As you can imagine, it's a difficult problem, because the first mapping, atomistic to coarse grain, is maybe many to one. But coarse grain to atomistic is one to many. There are many ways in which you could coarse grain so that you can get. So people have even tried things like carrying some information, but again there is a computational cost to it. So I want to thank you for asking, because I want to always, when people ask me and say, can you do this simulation? Actually that question has no meaning. The question is, what is a particular thing? If a phenomena, I was talking to Dilip today and said, oh, he was describing some procedure and said, you know, it is a very fast thing, it happens in 1 second. 1 second is in eternity for anyone who does any kind of simulation. So you have to first figure out what question you can ask and what level of detail is needed to answer the question. So my simulations are very generic bead spring simulations. So there is no mapping. So again, so this is the very generic bead spring model that I have, which is there is a connectivity and two things cannot come on top of each other, basically. That's it. That's the only ingredients that go. Of course, I also do charged coarse grain models, in which case they have charges. So this is the simple model that I have. If I'm interested in understanding the flexibility of it, I can include a third one as well. That's it. So this is a typical model that goes ingredient. Okay, so now we come to this problem, the main topic of which is that polymer collapse. You can, though I have used the word solvent, I want to explain that there are multiple ways in which you can make a polymer collapse. Yeah.
So when you do this atomistic simulation,
yes.
how will we know this atomistic potentials? Is it how we will know?
Okay, so again, atomistic potential. So you, so I've also worked in developing atomistic potential. Again, very intensive. You have to do quantum mechanical calculations. So first thing is, you do have some experimental input. For example, if I'm the first person trying to come up with a model for water, what are the ingredients I know? Whatever model I come up with, if I'm going to claim that I'm simulating liquid water, some properties I must reproduce. Density I should reproduce. I know 1 gram, so that information comes from experiment. You have a structure factor that experiment gives you. I can try to get that and match and get. I can get boiling temperature, specific heat. So these are experimental details, and how my model is more and more robust if I can represent larger and larger number of experimental details. That's the way I can. You would be very surprised. Water has been one model which is like, you know, it undergoes transformation every so often. Today, the most accurate water model, which has 3 atoms, is a 5-site model. So to represent 3 2 oxygens and a hydrogen, The most accurate one, which describes many property, is you have two oxygens, you have lone pairs, and you have, so you have a 5-site model describing a 3-atom. So now you can do that with water because it's a simple system. But if I am now doing protein, it's not possible. So there are ways in which this force field development in itself is a field. But very unfortunately, the beneficiaries of that field are the users. If you take a graduate student and who develops a force field, he or she will take 5 years to do this, and at the end of it, it's a very labor-intensive procedure. On the other hand, if experimental values are not available, you have to break down the model into smaller systems, and you have to do DFT calculations, try to get the energies. That also is equally expensive. How do you stitch back and things? So that itself is a whole field. There are groups which dedicatedly do, and I think they do a lot of service to people. That's all I can say, because it's a continuously optimization problem. You have to keep optimizing parameters to reproduce things. So, but today there are reasonably good force fields available to simulate proteins or anything. There are, yes. The problem today that we have, again, this is general information for people who may be interested in simulation, is earlier whenever the force fields were developed, because of the computational cost, you could not simulate for a very long period of time. Now with computation, you are able to simulate for longer. So people are seeing problems which you could not see earlier simply because you simulated for a very short time. So now, given the fact that we have computation, we are seeing the limitations of these force fields, which require that you need to continuously do something. Because as I said, if you can imagine, experiments are trying to come down in system size and probing as fast as possible processes. Simulations are trying to go this way. Can I simulate larger systems and longer times? The gap between them is huge. Good for simulation people. Huge. If experiments come down very fast, I suppose we'll all lose our jobs. Okay. So, as I said, you could collapse a polymer into many different ways. I want to take all the different ways in which you can collapse into one thing, which is increasing effective monomer-monomer attraction. However you can do that, it will lead to collapse. You could do that many ways. You can change temperature, you can change solvent quality. I will show something called depletion. You could have bridging. You could have something called co-non-solvency, solvency. Whatever is the phenomena, you could have external pressure, osmotic pressure induced collapse. Whatever be the mechanism, in the end, if there is a mechanism that increases the effective monomer-monomer attraction, you will tend to have a collapsed conformation. Okay, so that is the thing. Now, again, because of increase in computation, we are able to address questions like this. So this is a very nice phenomena to just show where it is. The typical image of a cell is cut. You take a small portion. Cell is an extremely crowded environment. Now, how do you know if it is extremely crowded environment? It is 40% filled with big molecules. Now, you can say 40%, is it crowded enough? You can go back to your simple solid state thing. So you have seen packing fractions in simple cubic FCC, BCC. Your packing fraction is of the order of 0.6 to 0.7, right? This is 0.4. So it's not crystalline, but it's very dense in compared to this. So you imagine you have all these life processes that are happening in an extremely crowded environment. If something happens in a very dilute environment, it has all the freedom to explore many conformations, many things, find its ground state and things like that. But everything in biology is happening in extremely crowded environment. As you can see, you can zoom down and you can see what is it. So the question what one wants to understand, because now computation is possible to simulate, in fact, I just want to point out to you that this is an atomistic simulation. It's probably one of the largest simulations that is done in terms of so right now the question is, we are only demonstration phase, in the sense we can do this simulation. So asking questions is still, I think, a bit far. So the question is, how does the Crowders modify this? the earliest model that people have tried to come up with, trying to understand how polymer behaves in a crowded environment, is something called a depletion model. Okay, this model 1954, Asakura and Usawa, this is very famous depletion model. The idea is very simple. Everything is repulsive interaction, right? And if everything is repulsive interaction, free energy, Helmholtz free energy, F is U minus Ts, which means you have an U, which is the interaction potential, and you have an entropic term. You have an enthalpic term and you have an entropic term. So let me say energetic, even better. Energetic term and an entropic term. So your free energy, which effectively determines what is a ground state or what is the equilibrium conformation of a polymer, is a competition between these two. Now if everything is repulsive, then U has no meaning because it only sets a scale. Then the thing that determines is entropic term. What is entropy? It's not disorder, that is the answer that is emerging. Entropy is just the ability of the system to sample as many conformations as possible. I want to maximize my choices, whatever ways I can. So suppose if everything is repulsive and I have a combination of, let's say, two large objects and small objects. Now you can imagine that these small ones will get more space to explore more conformations if these large ones come together and leave all the space for the small ones to go wherever they want. So which means what is happening in the terms of what I said earlier is, because they want to maximize their entropy, effectively they are increasing the attraction between these two large bodies. So there is no attraction. The actual interactions present in the system are all repulsive. But because the small molecules have an entropic gain, if they have more space, they tend to push the larger ones. You can imagine the same thing if you have a single polymer. If the polymer is extended versus if it's collapsed, you have more space available for the other particles to explore entropically. So there is an entropic gain. So this kind of, so they will deplete from the surface of the polymer or deplete from the surface of the macromolecule, and hence there is a effective attraction that is emerging in the system where none exists. You have not put in any attraction, you have put in only repulsive interactions, but there is an effective attraction that actually develops. So this has been used to explain many phenomena in biology, this depletion interactions. There's basically, you have a crowded polymer interaction are purely repulsive, and this is the thing. They don't collapse, they just come together, meaning they sort of aggregate. They don't collapse on top of each other because your repulsive interaction prevents that. But the question is, they just aggregate. They come together, but there is no. So effectively, that's what I'm trying to say. Everything is repulsive. All the interactions are repulsive. But still, if you have a system like this and there is a size difference, there is an effective attraction that is emerging where the big ones want to stay closer. So there is sort of a phase separation happening. But you have not put into the system. They are actually repulsive. So that is. Okay, so that is when everything is repulsive. But however, there are many systems, including biology, where crowders are attracted to the polymers. So there are attractive interactions. So the question is, if you have these attractive interactions, are they different from depletion? What is it that they do? What kind of conformational properties they do? So this is a known example of how you have you might have read about this. DNA is an extremely long molecule which is compacted into an extremely small space. That in itself is a question. How is it able to do that? Because as you may know, DNA is a negatively charged polymer. So you have a negatively charged polymer which with self-repulsion it should be as extended as possible, but it is actually compactified into an extremely tiny space. And one of the reasons that it is able to do that is there are something called DNA binding proteins, which is, now these are the crowders which like DNA. So you have attractive crowders, they sort of compact this DNA. There are many mechanisms, but this is one of the predominant mechanisms in which you can do. So why I am showing this is that this is actually what is a real phenomena that happens. We take motivation from this and then we try to ask the following questions. So this is something that was said in a paper in 1953, and this is very important. So Remember earlier I said if I take a polymer and put it to a solvent where the polymer, like solvent, it wants to maximize and it wants to be in as extended state as possible, right? If I just extend that idea and I keep increasing the attraction between these Crowders or solvent molecules and polymer, I expect at some point it should become as straight as possible and stay there, because that is the way it maximizes. But counterintuitively, if you increase, what actually happens is that it collapses. So this is very counterintuitive, because this is not what you expect. You expect that if it wants to maximize the attractive interactions, it should stay as extended as possible. So this scale, what it's showing is that if you have high intrapolymer attraction, it collapses. But that is only because polymer likes itself. If you have very low in polymer attraction and like solute, it wants to be in an extended state. But if you have these solute molecules, if the attraction is more and more, counterintuitively beyond a critical point, what we are going to show is that it actually collapses, and this is a new kind of a collapse, which is the bridging induced collapse, which is very different from the depletion induced collapse. And what I want to say there is, from the paper, the better the solvent, the greater the swelling of the molecule. Conversely, poorer the solvent, the smaller is the molecule. This is from the Flores paper, but that seems to be not the case. The more is the attraction between the polymer and this thing, after beyond a point, it goes actually from swelling to collapse. So too much of something is actually not leading it to be more attractive, but it's actually leading it to collapse. So this, the entire talk is just that slide. Okay. So to do this, what we try to do, again, as I said, very basic coarse-grained model. I have a polymer, M is the monomer, C is the Crowder. We are doing what is called an implicit solvent model, in which I have Crowders, but the solvent is not there. This I can modify it as by changing the interaction parameter epsilon mm. I can make it a weak polymer, self-interacting polymer, self-repulsive polymer, all these things are possible. And I look at different Crowder concentration and simply ask the question, how does this polymer behave when it is sitting in a sea of Crowders which like the polymer. Okay, so this is a first one of the results. What does this result? What is it that we are trying to show? Okay. When epsilon MC is the attraction between polymer and Crowder. Okay. When the interaction between Crowder and polymer is small, this is in some sort of a extended state. If your epsilon mm, which is a polymer-polymer interaction, is weak, the red one, this is in extended state. This is what is normal thing, right? If epsilon mm is 1, it is already in a collapse state. So when your epsilon MC, when the Crowder interaction is very small, it is behaving like a good solvent, bad solvent. Nothing, no surprises here. Now, let's look at the other extreme. In both cases, whether I take an extended polymer or a collapsed polymer, if I have extremely high attraction between polymer and Crowder, everything is again collapsing back. These are two extreme cases. Now what is happening in between? You can see very nice transition in which something goes from extended all the way to collapse. So what this essentially is showing is, if I have a polymer, and I basically am now seeing that, I'm trying to ask, what is a phase diagram of these things? You have an extended conformation, you have a collapsed conformation which has nothing to do with Crowder but only because polymer likes itself, and you seem to have another collapsed conformation which is purely coming because Crowder induced collapse conformation. So these are the three things, and this is how the phase diagram looks like. Yeah. Yeah. So that is I had shown earlier. We work in different. We also look at it as a function of Crowder density. So I'll show you the result of the Crowder density as well. So what seems to be happening in this case is, this is the phase diagram. Each point is a average of many simulations. So we simulate each of these points, many simulations, because that's what you should do for statistical results. And then You can look at these things and you can draw phase diagrams around these things. Again, I want you to draw this attention to what I was saying earlier. If I were to do this for a real polymer and put all the Crowders and try to get a phase diagram of how this behaves, this is just computationally an impossible challenge to do. But if I can take any generic polymer in which a polymer which effectively behaves like a neutral polymer and sitting in a Crowder with certain density, typically that is what this will behave, and I can get some physical insight into the system in which I can get things like phase diagrams and more importantly phase boundaries. Okay. So, I can construct all the phase boundaries in these things and get some insight into how these things behave. Then I can ask the question, I seem to be getting two collapse states. Are these two collapse states same or are they different? That is another question one can ask. And you could do more because of course simulation you have all the insight into the details. What you can look at it is that the first one, if you can see, the monomers are the closest. And if you see, look at this, there is actually, it's a monomer-crowder, which is the first pick. I'm assuming again you know what G of R is. This is nothing but paired distribution function. It gives you an idea that if I'm sitting, who are sitting around me? Basically, that is the idea that this gives. So, to answer your question, you can look at this at different densities. So, you can see that if you are at a low density, you can go from one phase to the other very smoothly. But if you, as you change the density, you have a reentrant mechanism in which the collapsed state first extends, all the Crowders come into that, and then it further again collapses back. So, density plays a huge role as to what in the phase diagram, what is the path things are taking. So, that is something that we can see. So, one interesting thing about the basic difference between the depletion mechanism that I told earlier and the bridging mechanism is that to get a depletion induced collapse, the size difference between the polymer and the Crowder should be at least something of the order 50, which means only very small Crowders can induce a collapse. But if I look at bridging mechanism, to get the same level of compaction, I don't need that small things. Actually here we are using the same size as the Crowder and they are still able to collapse it. So in some sense your bridging mechanism is much more effectively collapsing it. If the same size can collapse, as you can understand, even much smaller things can collapse better. And this is something that we probe next, where we look at things like what are the size effects. And very interesting things emerge. If the Crowder size is very small, then the Crowders are sitting inside the polymer. If the Crowder sizes are very big, then the polymer is sitting inside the Crowders. So what I'm trying to say is that who decorates whom is the question, and that depends very on the Crowders. So you can see the same polymer, red is the polymer. This is sitting inside the spaces, interstitial spaces of your big Crowders. If you take very small Crowders, all the Crowders are just sitting inside. So what I'm trying to say is that I can now use the Crowder size as a tuning parameter, and I can explore what are the different conformations that these polymers can take. And of course we have not done that, but you can imagine in biological setting you have a polydispersed system. So you can now have a mix match system of small and large, and you can span a large number of conformations that these polymers can take, and you could do explore many of these things. So basically the moral of the story is that the Crowder size does not simply change it changes the mechanism of the collapse. What collapses into what is something that is fundamentally changed when you change the size. Again, we can come up with phase diagrams. So I really want to emphasize that coming up with phase diagrams is one of the strengths of coarse-grained simulation, because we could do large number of simulations and actually very reasonably accurately predict the phase boundaries. They are not the exact phase boundaries, but we could reasonably predict. Again, we can see very different ways in which we can change the attraction, self-attraction in the polymer, or you can make it very attractive and weakly attractive. Many different kinds of phases the polymers can explore. Okay, so what we have seen so far, we've seen a neutral polymer. If it's sitting in a bath of Crowders, there is collapse mechanism that happens. We know how size can be changed. And now we ask a question, suppose if the polymer is charged instead of a neutral polymer, what kind of things that do these crowders do? So these are, charged polymers are very interesting because you can go from, when I say charged polymer, imagine beads of same charge on them. So this should be very counterintuitive that as I'm increasing the charge on the bead, it actually goes to a collapsed conformation. It should actually be as extended as possible. But that is because there's something called Manning condensation happens where counterions collapse onto the polymer. So whether it is poor solvent or good solvent, we've done a lot of work on these things in which we can show that very counterintuitive behavior happens. These are the counterions, which means if the polymer is all plus, your counterions are negative. So they condense onto the thing, effectively renormalize the polymer, and you can get into some kind of a collapsed conformations. I'll just say why this is relevant. This is, you can see, this is a DNA. You have an extended conformation, and actually you can see the collapse. So this is not something that, a theoretical model and people actually do see. Interestingly, all I want to say about this is that even if you take a charged polymer, which is not in the collapsed state, but which is in an extended state in which there's a lot of charge repulsion, adding crowders still takes it from an extended to a collapsed conformation. So what I'm trying to say is that whether you take a neutral polymer or a charged polymer, addition of crowder seems to have an effect in which when you have a large number of crowders and lot of attractive things, instead of the polymer trying to be, whether it is neutral or charged, in an extended state to maximize, it actually goes into a collapsed state. So the question is, how is it that it is doing? Basically, this is what is a bridging mechanism. You have all these things are decorating the polymer, and then now you have attraction between the things. So it is the crowder attraction that is effectively pulling the polymer closer, and then it is actually collapsing. So it is not the polymer that is collapsing, but it is the decorated crowder which is there, which you can do. Again, we can get these phase diagrams in which we can ask the question. You can, of course, in charged polymer cases, we can have valency of counterions. They have very different things. We can write down the equations of it and try to explain where from the free energy of these crowders are coming. And they can collapse charged polymer even when the electrostatic attraction keeps them extended. And for the last part of the talk, I've been talking about single polymer chain. Now we can ask a question. In general, in any of these systems, you have multiple polymers in a sea of crowders. How does these things behave? Do they behave very differently? If they're all extended, do they just be in a dissolved state, or do they go into some kind of aggregation? What kind of aggregation? What is the role of flexibility of these polymers? So these are the questions that next we'll be answering. What is actually one of the interesting things is that the critical crowder polymer attraction where a single polymer collapses is around the same critical where aggregation also happens. Now why this is interesting is that it seems like what is the mechanism responsible for collapsing a single polymer is the same mechanism that is responsible for bringing multiple ones, which means if you could do a single polymer experiment and understand what this critical thing is, you should be able to predict what would happen if you have an aggregate of these things. So this is something that shows up in when you look at, you can see what is the variance of the energy, and you can see also the exact phase transition where you have these peaks coming up, where a response function like this chi, it diverges, and then we can identify which is a collapse and which is this thing. Again, these are some things that if you had stat mech course, you would have seen these things, response functions being something that show where the phase transitions are. So, yeah.
So when you were talking about these crowders, if they are also same charge, crowders?
No, crowders are neutral.
Okay.
Sorry, I should have mentioned. Sorry?
If your crowders are also charged?
So then they would, you have some, there are, what people do is instead of crowders, you can add salt to the system. So what they do is that they shield the polyelectrolyte basically. And then maybe the aggregation mechanism would be very different. So here we are looking at only neutral crowders, charged polymer, and charged counterions present. That is the system. Again, I want to just show here some pictures where we start with rigid rods, and as you are increasing the Crowder attraction, you can see how nice tubule kind of things they form, and that is actually an experimental figure where actin filament aggregation is formed. You can see that these images where these kind of aggregations are formed for the rod like actin things are the conformations you can actually get from a simple coarse grain model. Now, why I am trying to show is that now, is this exactly why that happens? Probably not. That is not the claim I am trying to make. The claim I am trying to make is that you could take a phenomena like an aggregation of actin filament. Actin filament, if you know, it's a largely rigid polymers. So I can now make a question out of it, as in, if I take rigid polymers which are let's say neutral ones, this seems to be the actin conformation. So they are not collapsing like this, but they are forming sort of an extended structures. And you have a very simple model here which also is giving you some kind of an extended structures. So you could get some kind of insight into how these real actin filament aggregation can happen when you do these kind of simulations of very simple models. Doing that simulation in all atom is just not possible to do. If you change the flexibility of the polymers, you get different kinds of aggregation. So you can explore a lot of these things. I don't have the figure, but you have a lot of this biocondensate which actually look like this, where you have a lot of small aggregates that are forming. So you could use, what I'm trying to say is, you could use these models as platforms to understand different phenomena which are very difficult to simulate in all atom detail, but I can get the physical principles of it and simulate with very simple models. That's the theme that I want to keep focusing. Again, we can look at what are the kinetics of aggregation. We can measure the kinetics, and it seems like the flexible chains aggregate much faster than the rigid chains, because rigid chains, the way they have to do is that two rods come like this. First is an alignment problem, and then they have to align in this direction. So you have a lot of time that takes before they start aggregating. But your flexible chains are, because of their flexibility, they can keep growing as some kind of in a spherical n to the power of 1/3 way. So we could really look at these aggregations and say which aggregation is faster, how do you control the aggregation. Now I can use flexibility of the polymer as a parameter to control the aggregation of polymers as well. Anyway, so the last slide, it's already 5:30. I hope I've been able to convince that you could, Crowders are something that can induce collapse in multiple mechanisms. You can have it in, I have not spoken about confinement, but that's some other time perhaps. You could have depletion way of collapsing, bridging. The Crowder size determines whether the polymer is bridging, the Crowder is bridging the polymer, or the polymer. You can get all this insight into it. And you have the same mechanism that is driving collapse is the same mechanism that is driving aggregation of multiple. And I think the most important thing that I want to convey is that you can do a lot of these kind of questions you can ask through very simple models. These are not at all complicated models. These are very simple polymer models which the computational cost is not that much. You can do repeated simulations, get very good statistical averages, and get quite insight. So the most important takeaway is that what you should ask is, what is a question for which I can do coarse graining? It's not like I do coarse graining, so what is, you have to find the question for which coarse graining is the most appropriate one. And I think I sort of, I'll stop the talk with this slide. This slide, there's a thing called CCAM meetings that happen every few years. If again anyone who is in the field of simulations, Anisur Rahman is considered as the father of simulations, and this supposedly is a vision chart that he has written, possible things one wants to do. By the way, this is written in way back wherever, 1970s or 80s. And these are all the problems that he thought we should be possible to do simulations. Early simulations, they focused on simple liquids and polymers because your computational cost would allow you to do only them. Then your computers started happening, you have more things, you started doing all atom, but you are reaching a limit because there are certain phenomena all atom is probably too expensive to do. So we are sort of a resurgence of going back to these simple models, But now you're asking much bigger questions. You're asking questions like, how do membraneless organelles form inside a cell? Now this kind of big questions which are unthinkable to even think of. Polymer models, simple polymer physics is now able to sort of make a dent into these things and address. And so I hope you take away this thing that as a person who does all atom simulations, I'm saying this, you don't need the detail all the time. Sometimes, meaning it's like taking a big hammer for a very small thing. So perhaps you don't need detail all the time, and the wisdom lies in really understanding what level of detail is needed. And if your questions happen to be something that look at more organizational principles in general, I think simple models are excellent because you have a control, you can change models, parameters, you can ask many different kinds of questions, separate parameter spaces and get insights. I think there's nothing to look down upon very simple models. Simple models can be very, very effective and very powerful. So I think that's the message I want to leave with, and thank you. And these are a bunch of people I have been working over the years for this set of coarse-grained simulations, not all atoms are some other set of people, but I've been working with, and thank you. I don't know how you people stayed up. I would have, for a 4:30 talk, I would have absolutely slept through, but I cannot believe so many people actually are wide awake. Okay, so I'll be happy to take any questions if you have.
Can I ask?
Yes, yes.
So you started the motivation of this, like there is a cell and then, but it seems in your simulation you did not consider like confinement.
Yes, I didn't show here, but I do simulations where confinement plays a role. For example, a lot of adsorptions can happen on the cell wall. All those things also can be done by these polymers. I'm not shown those simulations here.
And these things basically kind of happen in the bulk of the...
Yeah, so you can have this nucleation thing, you can have spreading of polymer chromatin on the cell's nucleus surface. All these things are possible to do. Yeah.
Crowders, you said that they are neutral. So what drives this breathing? It is still entropic gain that drives the breathing?
No, it is enthalpic. Basically, basically you have your polymer like this, you have these things that are decorating it. Now, if the attraction between this and this is a parameter you can control, these two are trying to come close. But since they are now adsorbed onto the polymer, they are bringing the polymer along with them. And the important thing is, it's a Crowder-induced polymer collapse. The polymer is not doing anything here actually. It's because if I change from good solvent to poor solvent, it's the polymer that is doing the work. Either it likes the solvent or it likes itself. But here polymer has no role. It's the Crowder that is, I'm using Crowder thing as a thing, and I can tune this. So beyond a critical point, too much of a good thing, they want to come closer. So then there is a collapse that happens.
If you visualize it, let's say in an experiment,
Yeah.
you want to tune this crowder interest. How do you do that? Because they are all neutral, right? And
That
so
is
get
true.
charge.
That is true. So we have been trying to, how would you increase the attraction? No, because people do these DNA experiments in which they, but I am not very sure how should one increase. Yeah, so many things. You can have polydispersed things, because that's the, if I want to really simulate cell environment, I should have polydispersed Crowders. That is actually the reality. So, yeah.
The scaling laws that you suggested at the beginning, right? Do they change in presence of Crowders, or they all?
No. They don't seem. So, for example, if I take a polymer collapse because of self-interaction and a collapse state of polymer because Crowders are there, it's still n to the power of 1/3.
It's just that the Crowder has an the
That's,
collapse.
so basically it is effectively increasing the attraction. So again, that point that I said, that in any mechanism in which if there is an effective increase, however that effective increase in attraction is coming, there is a collapse that seems to be happening. And in this case, in my free energy term, I just have another free energy with the Crowder. That's all. So the scaling laws don't seem to affect. It's still n to the power of 1/3. Yeah.
Just wondering about the relationship with experiment.
Yeah.
For example, your phase diagrams. How close are you to what people can see in the experiments, or how would you build an experiment to check?
Very honestly, I don't think these phase diagrams exist. We can probably pick points. I can pick a point in an extended state. For example, I've shown you the DNA collapse. So I can map an extended DNA into the phase diagram somewhere and a collapsed one somewhere. But can I exactly map the interaction energies that take it from extended to collapse? Probably very hard. Yes, so again, as I was answering someone, I think to answer those questions, perhaps a little more detailed coarse graining may be needed. But I think these models just give the physics insight into that thing, that if you have something and this, and you see what could be the possible ways in which this collapse can happen. But if I want to really take, let us say, a DNA and do, either I have two choices. One is I have to do all atom, it's very expensive, or I have to do a very detailed coarse graining to capture DNA and then do, and then get my phase diagram. So it's just insight versus computational cost. I think we are stuck somewhere there. Yeah, I'm not sure if the machine learning kind of things will be able to take this to another way in which you can do multiple small simulations and it can figure out a path in which you could effectively simulate. I do not know. Could be, I do not know. But I think machine learning is popular enough. I don't want to add it to its popularity. It's already too popular, yeah. So, but perhaps that is something that could, but it is just extremely expensive. I think that is the thing. So for example, an all atom simulation, like I do, I'll tell you an example. You have a protein, I make a change mutation, and I want to see how it behaves. This is the question I want to answer. I would need, assuming that this is about a 1 microsecond simulation, which is probably nothing in terms for experimentalists. If I want to do a 1 microsimulation a second of this, I need 512 cores and probably 3 months. I'm talking about wall time. That's what I need for one simulation. Now, if there's a reviewer sitting and saying, oh, how do you know this is true? You know, you should have at least 3 replicas, which is very easy to ask as a reviewer. But then you can multiply how it is. Exactly. Now, if I do coarse graining, for example, I could do the same system. Maybe I can coarse grain, and I could do on a 12 or a 24 core machine. And instead of 1 microsecond, I can get maybe 10 1 microsecond multiple simulations, probably in a month's time. But that doesn't mean I can coarse grain everything. So I have to make a judicious choice as to what is the question. Can I coarse grain and still give physics? But some question like a hydrogen bond induced binding of something, I have no choice but to do all atom. So now, as someone who does all atom and coarse graining, I always have to ask this question of trade-offs. What is it? So that is what I mean by expensive, and it's really expensive. Yeah. Okay. Thank you. Thank you. The violet second law.